Thank you. Thank you everyone for being here. It's my pleasure to have a brief introduction to Berkeley after the pandemic. Glad to see all the interactions happening over here. So today's talk will be very in QI flavor compared to I think the form of this group perhaps. So bear with me and let's go through the last questions of the talk. So this one is work based on this archive over here with Hassan, Alex, Young, and Zoltan Zagorov. And it's about overlapping cubism with the tensor network. And in this talk I will explain what these words mean. So let me start with a question. It sounds like a dumb question, really. So if you're handed capital N qubits, how do we know that they live in two-dimensional Hilbert space? And of course, it sounds like a no-brainer. Of course, they should live in two-dimensional Hilbert space, right? So maybe let me first be more precise what I mean by qubit. So let's take some Hilbert space, and then you can factorize some two-dimensional subspace and whatever the remaining junk. You can define some Pauli operator, or a really unitary operator that has non-trivial support over this two-dimensional subspace, and call it one x and call it z, such that these two anti-commute, and that's a qubit. So for example, this is the conventional qubit, right? So you have just x tensor I and z tensor I. These two operators form a pair, and then that defines a qubit. But in this definition, the following operator is also a qubit. So if you just choose the same basis, and then you have x tensor x and z tensor e, z tensor z, they also satisfy the anti-commutation relation, and that also defines a qubit. And of course, these two qubits, so to speak, they don't really commute, right? So if you take x1 from the first qubit.
I'm totally lost here. Why wouldn't you define a qubit just as a two-dimensional Hilbert space? What is the c that we're factoring out here? Is that too complex dimensional?
Yeah.
So that's the first qubit. And then h prime is the other qubits?
H prime is whatever it is. Yeah.
So you're defining one qubit and the rest of the world?
Sure. Okay.
And these tensor symbols, they refer to which factors of the Hilbert space? Because you have two factors in the beginning, but now it looks like you have three.
So in this example, you can think of this as, C tensor C, or C2 tensor C2. So you can think of an 8-dimensional Hilbert space. You can factorize it into 3 factors, right? And then...
Oh, H prime is C2 tensor C2. Yeah. So the whole thing is 3 qubits.
That's right. Yeah, in the example. Yeah. And why would you care about this? Yes, that's on the next slide.
What you're doing is you're defining, what's the point of defining these operators? Are they like qubit operators that make use of multiple copy? So you can break up the Hilbert space in different ways, is that the point?
That's sort of the point. Yeah, we'll see that in the next slide, why this is important. Yeah, that was a great question. So, but of course, if you really have these qubits and then the commutators, xi and zj, they're always vanishing, then of course this is the case when you really have n independent qubits, right? And they really live in two-dimensional Hilbert space. And that's the conventional intuition I have about qubits. But now, let's think a little bit like an experimentalist. Suppose you walk into your lab, you turn on your machine, and you have all these atoms that you trap in your setup. And then you can isolate some 2-level system on each of the atoms, and you call them qubits. But usually what happens is that if you manipulate some atom over here, it would inevitably change the state of some atom far away as well by just a little bit because of long-range interactions. And it's possible to map these sort of interactions as a slight non-commutation. So if you think of I as, say, labeling this first atom over here and J labeling the second atom over here, doing something to I influences a little bit of what's happening to J. So there is like a slight commutation non-commutation as captured by these, approximately independent qubits, but they're not exactly. And that's, we're coming back to Raphael's earlier this question. So if I actually focus on these physically motivated scenarios, how I identify qubits are based on what kind of operations I have control over these atoms. Right? And there's the fact that the theorists tend to think of them as living in separate factorizable Hilbert spaces is not identical to what people actually do in these. So if you are actually experimentalists, and then you have control of all these atoms, you would expect that they have some small overlap, but it's actually kind of hard to verify, how large this commutator is if epsilon is very small, right? For example, it's below your experimental precision, it will be difficult to verify that the commutator actually is 0. But even just in principle, suppose your experiment is absolutely perfect, and you want to go out there and to verify that the commutator actually is 0. What would you do? You would, instead of measuring the commutator, because we never really measure commutator in experiments, we measure this operator with respect to the state. Right? So all you can verify with each state is you can verify that this thing acting on the state is 0 for each measurement. Right? And then you're going to have to, and if you want to verify the whole commutator is 0, you're going to change it into another state. Measure it again, make sure it's 0. Change it to another state, measure again, make sure it's 0. Now, if you're unlucky, and then in principle, you can take out to 2 to the n number of times before you actually verify that this thing is actually identical to 0. So the point here is that if you have these overlapping qubits, which is the thing that we sort of physically expect to happen in the lab, they overlap in practice. So it's not some just completely crazy pull out of the thin air idea. And it's hard to verify that they overlap in practice, and it's hard to verify that they overlap in principle. So, yeah.
This overlap is a nuisance, right? If you're trying to build a quantum computer, it's a thing you don't want.
Exactly.
And wouldn't you just notice it from the fact that your computer isn't working?
Exactly. So, I'll talk about it here. So that's exactly right. There are protocols that will allow you to detect whether you really have an independent qubits or not, and those will be important, and later we'll make some analogy to gravity as well. So why should I care about these overlaps, right? Because as theorists, I just say, well, they're close enough to the n-dimensional number space. So I shouldn't just worry about it. I should just write down my usual Hamiltonian and my spin models in the way that I have an independent qubits. That intuition served us well if small changes lead to small problems, right? So usually in physics, we're used to the fact that I perturb the system a little. The prediction of this perturbed theory would be very similar to the original theory, up to a little correction. Here, it's not that. So it's remarkable, it turns out, that if you allow the qubits to overlap just by a little bit, you can actually compress capital N number of qubits into small n number of qubits, where this capital N is actually exponentially larger than small. This is related to the fact that in the vector space, n-dimensional vector space, there are exactly n mutually orthogonal vectors. So analogously speaking, let's think of each such vector basis as an independent qubit. So when the vectors are exactly orthogonal to each other, they correspond to independent qubits.
So isn't the statement that you can only fit simple states of these big M qubits into little vectors?
Yeah, right now we don't have simple or complex.
But then I thought this.
We're fixing a state here. We're fixing a particular state. Sorry. Wait, you're wanting this to be true for all psi. You're wanting the O's to be independent of psi here.
This is true for this construction.
But if you're fixing that for all psi, then you're fixing the norm of OIOJ.
Well, yeah, you're fixing the norm of OIOJ.
Yeah.
In this particular construction. Later on, I'm going to talk about the sliding table construction. But coming back to...
So this is a different construction than what we're doing with non-isometric codes.
Yeah.
This is like fixed degrees of freedom, but yeah, anyway, I don't know.
If epsilon is equal to minus s over 2, or epsilon is square root n, that's usual typical state, just all essentially e to s approximately.
Exactly. That's precisely the... Yeah. So the fact that you can... These small epsilons lead to big properties exactly because you can fit e to the n number of approximate orthogonal vectors into an n-dimensional vector space, but you can only fit n even vectors into exactly orthogonal vectors. So this idea of approximate orthogonality has been around known as Johnson-Lewis-Strauss lemma, random projection, compressed sensitive dimensional reduction, and a bunch of other things in different fields. More recently, this general idea of approximate orthogonality has also found its way into high-energy physics. And this is one of the papers that inspired our work. But there are also others.
So this, in the Chow, Reinhardt, Sutherland Biddick paper, then epsilon is order 1 over square root little n or something, right? Like so it's quite large. That might be helpful for you, Raphael. There's significant overlaps between each of these.
Yeah, that's right. So the point here is that we gotta sort of unlearn a part of our intuition to be careful about these small changes in this particular context. So you can, the lesson is that, of course, we can be fooled into thinking that the Hilbert space is a lot larger than it actually is, right? So you really have two to the small n-dimensional Hilbert space, but you think you have a larger number of qubits. Yes.
Yeah, I have a question. Before going to high energy, if you are just a quantum computing person, then the problem with this would be something like, I have a quantum computer, I think I have a lot of qubits, actually, really few qubits. But if you try to simulate a quantum system on that computer that has, say, an n number of qubits, then shouldn't you not be able to do that if you have this?
Yeah, that's right. So there is so precisely that one can write down. So it's obviously not true that I can compress somehow a large n number of qubits into small n. So eventually this approximation breaks down, and it depends on what things you measure and what things you do, you will find out it breaks down. For example, there are these protocols that these guys constructed, which is polynomial going in the big N, that allows you to identify whether you really have the qubits or they're just fake. Now let's come back to gravity. So essentially what happened over here is like some degrees of freedom counting protocol or degrees of freedom counting problem, recall information. But we also have a degree of freedom counting problem in gravity, right? So so if I just write down effective field theory in 3 dimensions, and let me laticize my space into the lattice points and put a qubit on each lattice site, of course you would naively expect the number of degrees of freedom to scale volumetrically. But quantum gravity tells us that that's not the case, right? For example, from black hole tomography, that really is just scales in areas of surface. So the question is, well, how do I reconcile these two ideas? And we live in the bulk. We like to think that the bulk experience is very much local and very much real. So the proposal here is, well, maybe we can think of these bulk qubits that we're putting on each lattice point and that scales volumetrically as overlapping qubits instead of exact qubits. So it is in this way that you can compress these apparent number of degrees freedom into a smaller Hilbert space. And of course, you have to give up something. So for instance, in this case, by overlapping, you literally just give up this microcausality, rather than you have some operators that are space-like separated. Instead of having the commutator be identically 0, you have it to be some small number acting on a particular state. But coming from a quantum gravity point of view, this is not entirely crazy, because when you couple things to gravity, then you use both unperturbative and non-perturbative fronts. You do expect these things to break down. And in fact, it's pretty hard to create completely isolated qubits. And then we can also ask, well, how do I find out that the number of qubits that are scaling volumetrically is fake? Can we also run like a verification protocol? And yes, sort of. So one verification is that let's try to access some of the states that we think are there, but actually are not there. Right? Suppose I try to excite the field theory a little bit everywhere and create the state that has low energy density everywhere, but it will violate the Bekenstein bound in PIR. Then gravity says they should collapse into a black hole, but EFT tells you that this state is something that you can create. And obviously there's a conflict. In nature, we observe that gravity, that we observe black holes, so it would tell you that the true number of degrees of freedom is not what you thought it was. Okay. Any questions about these?
How small does epsilon have to be for the gravity things?
Great question. No, we don't know.
I mean, my worry would be that it's not, a fixed choice of epsilon isn't going to work on all scales.
That's right. Yeah. You guys are very good at predicting what I'm going to say next time. So the question is, suppose we apply this idea to quantum gravity, what are the physically relevant ways to overlap these things such that it has a chance of working? So how small the epsilon has to be, how should I overlap these degrees of freedom, and is there a way to overlap them consistently such that it solves our degrees of freedom count problem in quantum gravity?
What happens if the theory overlap or it's equally minus S?
Yeah, I was just asking if that's sufficient for solid work. So is it just non-perturbatively small?
Yeah, so in this case it's non-perturbative. Later on we'll see that it really depends on how you overlap the qubits, but right now if you just use these mappings, it's going to be non-perturbative. Okay. Right, so the point of this talk really is to bring this sort of perspective into the conversation. We'll pose some questions, we'll try to solve a few of them, but really you should think of this as a starting point instead of the ending point. So I won't have all the questions won't have all the answers to the questions today. But the point is that so far what we've seen is this construction by Chow et al. They have a particular way of constructing these overlapping qubits, and essentially, there's no reason why it has to be true because the thing that they create is very strong. You have this to be small epsilon for every single state, and then the overlap is pairwise constant. So all the qubits have the same level of overlap, whereas does that really make sense in gravity? Maybe it should have some sort of distance dependence, right? Because we look at perturbative quantum gravity, there sure seems to be a big dependence that we have addressed. Okay, so and the other thing is that we want these overlapping degrees of freedom to at least be able to produce something that we can predict in the EFT. Right? So they should approximate the local observables. So if we ignore the fact that they actually have overlap, does this theory now look like a local perspective field theory? Right, so those are some of the questions we would like to talk about here. So the outline of the talk really is we're going to try to construct some of these overlapping qubits using a slightly different method than the one I just talked about. I actually haven't told you how they overlap the qubits yet. So. And then we're going to look at what are the limits of overlapping qubits. So we're claiming that, okay, you have some small Hilbert space, perhaps the quantum gravity Hilbert space, and it's supposed to simulate or supposed to give you the illusion that you live in a larger Hilbert space, but eventually this illusion breaks down. So when does the illusion break down? And when it does break down, what it will look like? So there's some of the So that would be this section, and then later on we'll apply this to this other mirror to electrical cosmology. All right, so first, overlapping qubits from symmetric maps. Sort of, as I mentioned earlier, this talk is very much inspired by these two works. So how do we identify these overlapping qubits? We're going to use them, we're going to construct them using non-symmetric maps. So these are just linear maps going from some Hilbert space, a subcapital N, which is, let's just take it to be 2 to the capital N dimensional Hilbert space. So we really have capital N number of qubits. And we map it into some smaller Hilbert space with 2 to the small n dimensional Hilbert space. Now you can identify some operators in the large Hilbert space, and then you can sort of project these large operators in the large Hilbert space and the operators in the small Hilbert space. So if this operator is some qubit in the large Hilbert space, we call it the overlapping qubit in the small Hilbert space. That's essentially what happens.
So Q here I should be thinking of as like a single qubit operator in the large Hilbert space?
It depends on the problem we want to solve. For now, we can't think of it like that.
So if I have something like that, I would have thought that QP is just proportional to the identity.
Sorry, the what is?
I would have expected QP to just be proportional to the identity.
This one proportional to the identity?
Say it's a Pauli Z operator on one qubit, right, Q, then it's like +1 times the projector onto the half of the Hilbert space, plus -1 times the projector on half of the Hilbert space. And both of those, when I conjugate with V and V dagger, like taking some much larger Hilbert space than HN, and we're sort of randomly projecting it into HN.
The key is randomly, right? So answering, if you do random projection, I think, and I agree with you, I don't think that's quite right, because we'll see later on, but if you don't do random projection, then that is definitely not random.
Okay, but I think if you... Okay, let's keep
going.
going.
Maybe let's keep going, and then we'll perhaps resolve some of those questions along the way. But graphically, what this map is doing, I like to think, is that you carve out these qubits in the large Hilbert space, and through this compression map, you map them to overlapping qubits in the small Hilbert space. So here's one example. I think perhaps this is what Jeff had in mind. Maybe it is not. So in this case, you can take some X operator. So Q here would be an X operator in the large Hilbert space, and then or Z operator in the large Hilbert space. And then you run it through some projection, some map here. So V is a non-symmetric map, where you just have a bunch of, and you have n qubits, you scramble it, and you project a bunch of them to 0. And then you construct the overlapping qubits in this way, so that you can compute a commutator between X and Z. And this is a numerics for very small sites. You can actually see that for thing. So this is I increasing J, right? So when I is equal to J, they don't really commute, of course. But when I is not equal to J, in the effective picture, of course, they were supposed to exactly commute, so this thing is 0. But when you project it onto the small Hilbert space, they don't commute, but they don't commute by a smaller amount than exactly what they would say.
What do XP, so this going back to my previous question, what do XP and ZP just look like here, just on their own? Like just the norm of XP, and in particular the difference between the norm of XP and the trace? Because I would have really strongly thought they're just going to basically be the identity plus a small amount of noise.
Well, I don't have the data here in my mind, so
okay.
Go back. We can dig through the code and then see what it outputs. The point is that the small thing actually matters. Yes.
I was asking, couldn't that actually be the case in the large n approximation? This is an equals 10, then you have the diagonal.
Yeah.
So
when you take the small n to be approaching large n, you would definitely have
yeah, if you take large n to be 100, it might be that it's nearly.
Yeah, if you take large n to be really, really large, then this thing will be featureless. yeah, would look like that.
And isn't that the limit you were thinking of?
Yes, but I expect it will be exponentially decaying in big N minus little n. So
Even when they're so close to each other?
yeah, I mean, it's like e to the minus 4, you know, maybe the prefactors maybe matter there, but yeah.
So the
Yeah, go ahead.
Yeah,
so I think the errors are going to scale.
it's maybe 2 to
as-
the minus difference of 2, so maybe it's 2 to the minus 2 is not that small.
I'm very dumbly confused. You mean the paper, one of the papers by just Akers and Pennington, or you mean the 5-author paper on
We talked about it both. Like it was discussed more in the 5-author paper, but the same model appeared in my paper with Chris on quantum minimal surfaces from quantum error correction.
That one, okay. Yeah.
So that was a random map, but you can also think, what if I don't want the non-symmetric map to be random? In this case, you can also reconstruct or think of an example where the overlap instead depends on the distance between I and J. So in here, you can take V to be you can think of having some 1D Ising model, and then you construct V such that V sends all the higher energy eigenstates to 0, but it reserves some of the low energy eigenstates. So that constructs the V, and then you can construct overlapping qubits in a similar way, but now you see that the thing on the diagonal is very non-commuting, but this non-commutativity sort of falls off as a function of distance. So this is a different way, of course, of overlapping qubits, but there are many other ways, right? It really depends on what V is. So now let's talk about, suppose you have V, then what are the things that will get approximated and what things will not get approximated? So when things are getting approximated, we call it spoofing, right? So you have a small Hilbert space, but you're trying to create the illusion of a large Hilbert space. So when that happens, it's spoofing. And so and then there are two cases where the approximation really is working very well, but there are also cases where you deviate from the approximation. So first, let's revisit this older example of the commutator, right? So if you take two space-like separated observables, it really is supposed to commute, but you can look at their overlapping counterparts. If somehow they also commute roughly, then we say that this commutation relation is being spoofed by the overlapping qubits. But of course, this is not the only thing you would like to spoof, right? More generally, you can have some endpoint correlation function in the effective theory, and you want this to be approximated by your smaller system. And well, when are you able to do that? So this is a sufficient condition. So if psi is not in the kernel of this non-symmetric map, and that this Q operator Q does not take you into the kernel, then you can show that this relation holds. So this is a sufficient condition for when the small Hilbert space diffusion field can actually reproduce what we see in larger Hilbert space. So just to give you an example, right, in the one that we saw before, if you construct a non-symmetric map by energy truncation, such that you map all the high energy states to 0, then Q are basically the low energy processes. They don't map you from low energy states to high energy states. They map you within low energy subspace. In this case, these processes with this kind of state, psi, and Q, then you're fine. Right? So those are well approximated.
In the original overlapping qubits papers, the Pauli operators for the overlapping qubits were meant to be Paulis in the sense of having trace 0, for example. If you go to a low energy truncation, at least in a very naive model, it seems like you're going to have, say your Hamiltonian is just sum over z's, and you've truncated it so that the total number of ones is less than some k that's much smaller than everything else. feels like the size of the projected eigenspace, where some Pauli is in a 1 state, is going to be a lot smaller than the size where it's in the 0 state, because sort of more of the remaining qubits are allowed to be 1 if the thing is 0 than if it's 1. Does that sound right?
I don't know how it will apply to the original overlapping qubits because we're not in that.
Okay, yeah.
We can definitely discuss more later on.
Okay.
Yeah. So as a second example, right, if V is hard random, then really if you take Q's to be low complexity operators and you take psi to be low complexity states, then those are called observed processes. You can't really tell that your space being spoofed if you restrict yourself to those things. But it's also interesting to understand how we would deviate from these well-approximated cases, right? So if you, for example, you can rewrite the commutation relation as between overlapping qubits as something that's coming from the effective theory plus a correction. So if Q and Q prime are space-like separator observables in the effective theory, that's equal to 0, then you can see that this overlap is really non-zero, but it depends on this operator T, which depends on Q prime and that kind of thing. But it's interesting to look at this for the reason that if this thing is, if T acting on a state is small, then obviously you preserve the commutator very well, so you preserve this notion of binding causality very well. But at the same time, if T has some spectrum, right, so you kind of think of the eigenvectors and eigenvalues of T. So here's an example of T if the non-isometric map is coming from this low energy conformation. So in this case, T actually has a bunch of 0 eigenvalues, which means that if you just choose a state at random, and then you ask how well is this commutator preserved, chances are it's going to be preserved very well. But there are also these larger eigenvalues, which means that if you take some other state, the commutator is completely gibberish. The commutator is large, it's not 0. So here's an example of these eigenstates as a function of energy. So if I take an eigenstate that has a 0 eigenvalue for in this T, then it has low energy. You can see that these bunch of states, they all have low average energy. So these are actually the states that sort of well preserve the commutation relation. But if you take some of the states that have higher eigenvalues, you see that they don't really preserve the commutation relation. So there is this notion of state dependence really coming into the picture, and it sort of makes sense from a gravity point of view, right? Because you need a vacuum state, and of course they preserve the macrocausality of the vacuum geometry, but if you now put in some really heavy state, then they can curve the underlying space-time direction. So that's sort of a QI analog of that. If you just use overlapping qubits, you get this for free. We can also do the same for the hard random projection. So again, you will see that there are a bunch of different eigenvalues for this T. Right? So again, you will have state dependence. So for some states, this commutation relation is well preserved, for some it's not. But if you just look at the states that preserve the computation well and the ones that don't, that they actually look very similar, at least you can't tell them apart, because they're all hard random states. You look at them, they all look the same. So it's very different from this energy transition.
So you can't even distinguish them as a complexity criteria?
We don't know how to compute complexity efficiently.
See, that's what you mean.
Yeah.
Right, the spectrum should be a semicircle if you're to compute it analytically?
That's a great question. We have not computed it analytically, though it can be done. For the numerics, it doesn't quite converge to a semicircle. It's very
Okay.
Yeah. That's a good point. So sort of to briefly summarize what we've seen so far is an analogy between the QI facts that we see in overlapping qubits and the gravity facts that we see in this, that we would like to think about in effective field theory plus some weak perturbative gravity, right? So we have overlaps in the QI thing, you really have perhaps this microcausality evaluation, and the spoofing is sort of approximating the EFT predictions. But when you go away from this perfectly spoofed limit, you also see like the state dependence, which look a little like gravity back reaction machine in your geometry. But of course, spoofing is not without its limits. Eventually, you can have things that break down all over one. So maybe that's what happens in black holes. But in this talk, we're going to focus on the de Sitter space. In very late time in the de Sitter space in this model, you will see that this thing will become over one. That's where there's strong breakdowns of this spoofing. Right. So at that point, perhaps you want to rethink locality. Am I already over time? Okay. Great. So just to briefly review de Sitter and tensor network. So on the left, everyone is familiar with this, right? It's just the 1 plus 1 de Sitter conformal diagram. So here I have the spatial extent parameterized in theta, and 2 pi is identified with 0. And you can have some observer that lives on the north pole, some observer that lives in the south pole, and their respective causal wedges their static patches are sort of just labeled in gray, and the horizons are dashed lines. And the time is going upwards. Right, so that's the conventional 1 plus 1 de Sitter. And on the right hand side, we have the Mera, which is a tensor network, and it's a map from a small Hilbert space to a big Hilbert space. So each of these lines, you can think of it as some Hilbert space factored degrees of freedom, or think of it as a qubit or a qubit. And each triangle is an isometry. So you contract two triangles, it gives you the identity operator. And each box is a unitary. But the point is that if you stare at this diagram hard enough, you realize that, hey, wait a minute, this looks very similar to the top half of this conformal diagram. And you can put the Mera on top of the conformal diagram, chop it in half. And you see that it reproduces exactly the causal structure that we expect for de Sitter space. For example, if you're an observer that's following a timeline trajectory, you would just stay within this causal patch. But as soon as you leave, there's no way you can ever come back. So this is the structure of a cosmic horizon marked by these dashed lines. And another feature that we notice is that the Mera is very coarse-grained. So each of these tensors is actually sort of a Hubble scale granularity. So the size, Hubble time, and Hubble radius. And each bond dimension, in order to make it match onto the de Sitter space, you really need to take each edge or each qubit to have a very large dimension. So each dot that you see over here actually has dimension e to the s squared. So it's a very large quantum system, but very close. So just a brief review on the Mera side. You actually, if you look at this Mera as the time model for the de Sitter space, it actually kind of reproduces the constant O'Hare theorem, right? So if you focus on the stuff that's happening within the causal patch, each time step that happens actually corresponds to a quantum channel. And this channel is contractive, so it means that eventually whatever states gets fed in at the beginning will converge to a fixed point. So this is very similar to what we see in the de Sitter space, where everything eventually converges to the thermal state, no matter what you put in at the beginning. So this is sort of like a tensor network primal with that. it's pretty obvious that this de Sitter tensor network is capturing the global structure of the de Sitter universe, where the apparent degree of freedom actually increases exponentially, right? If you look at the exterior region, it really doubles at every single time. So the question we would like to tackle here is, this is sort of like an effective theory, an effective description. Right? If you were an observer, you can fall into the exterior and then things will look real to you. However, there's sort of an idea within quantum gravity that we would like to think of the de Sitter quantum gravity over space to be finite dimensional, and this is e to the s, where s is the de Sitter. So how do I reconcile these two ideas? Now, on the one hand, I have really an explosion of the number of quantum degrees of freedom over time, and the other one really is telling me that my Hilbert space dimension is finite. So of course, we're going to use overlapping qubits. So instead of having real qubits that pop into existence, we're going to say that all these qubits you saw in the this future time slice that look large is actually all overlapping. And how to construct them? Well, all you need to do is to think of this as an isometric map. So you can.
Sorry, so each Hubble volume is now represented by just one qubit?
No. It's represented by roughly S qubits.
But the overlap is what's important is the overlap of S qubits here with S qubits there, not of the qubits within one group of S qubits.
Yeah.
So I might as well think of one per third. Is it important that I think of S qubits in horizon volume for your discussion? Because you're not drawing them like that.
Yeah, I'm not drawing them like that. I can really draw one. Each line you should think of them as having S qubits.
Okay.
Right, so the obvious idea here is to turn this map backwards, right? So you really are mapping all of these degrees of freedom into a smaller Hilbert space, where the smaller Hilbert space is isomorphic to the true quantum gravity degree. So now, you can again compute the overlaps of, let's say I take some operator in this patch, and then I look at this overlap with some operator over there in the other patch. Their size is going to be order actually epsilon divided by some function, power law function that depends on the separation between these two sites in terms of power distance. Yes.
Why do you think of the initial slice, which I guess here would be the direction symmetric slice, as the fundamental quantum gravity degree of freedom?
Oh, it's just in this particular case, when you take the zero case, that's exactly the right counting.
It's the one that constrains the entropy the most.
Oh, okay, right. So you're just assuming that the number of quantum degrees are freezing by e to the s.
Yeah. Well, in this case, you actually double it because they have two patches. But,
Sure.
Yeah. Right, so because of this Mera tensor network, you can actually show that the overlap, again, is sort of falling off as a power law instead of just constant everywhere. And actually, this is very similar. So this is the Mera overlap, and this is the Ising overlap. So you can see that these two are very similar. Of course, because Mera is supposed to simulate some CNT ground state, so when the critical Ising is the CNT ground state, so the fact that they have similar overlaps and also
I think I'm comfortable for you to go and pick one of these great time slices and make up some rules on what the overlap is. It's also finite, I guess, it depends on the distance. But you don't then get to make up an independent rule for the next time slice down, right? At that point, everything should be determined by the first choice. Otherwise, you seem to have so much freedom that you just make anything.
Yeah, we fixed the Mera, so we fixed the structure that we insist that this semi-classical description always have this particular concept.
Yes, if I run this back, right, and I fix the overlap structure on one slice, should I completely determine it on the next slice, given that you know what the network is?
You sort of, yeah.
Good. So you're not independently choosing it again on the next
No.
Yeah.
These are also correlated.
The reason I'm asking is that you wrote epsilon of t, and so there seems to be something time dependent upon your choice.
Exactly, because at late times there are more qubits, so the whole map's going to grow.
What is epsilon of t?
But, yeah, I guess the epsilon t better be consistent with what we know about the network, right? We don't get.
Yeah. So epsilon t is basically some function times e to the minus s, and then times something that grows exponentially.
So you know the behavior as a
You know the
t
behavior.
for this specific.
Yeah, exactly. For this specific. Let me skip. Well, okay. This slide is basically saying that if you take this capital T to be some very small number, right, then epsilon t is actually small. So in this limit, you actually can show that all that these sort of correlation functions are being lost. So any function correlation function lost. Yes.
Sorry, in the previous slide, in the figure you're showing on the right, that this doesn't look to me like the ground that you have over there. It looks like you have these big blocks where the areas are all the same. Like what? Is it the same?
So because of these discretization, so in the exact Ising model, you have translation symmetry. In this case, you can see that the tensor network is not exactly translationally invariant. So these blocks are associated with the fact that you have this symmetry. Good. So if you are in early time, you can actually show that there's a sense in which you can spoof these effective field theory very well. But this can't last forever because we're squeezing all these theories from the into finite over space. So when do you run out of space? So using this Chavada as a heuristic, although this is not completely correct, but the counting sort of works, right? So because there you expect to be able to compress exponentially many n's into this finite over space, right? So it would heuristically would take time to linearness before you run out of space. And indeed, in an independent Mera calculation, you can verify this by using the structure of the Mera. And you can show that this t, the epsilon becomes order 1 when t is roughly when this time is roughly linear in this entropy divided by 2m, and m is the m-plumb correlation of electric. Incidentally, this number, S over 2, actually coincides with whatever they derived in using slow growth inflation, but there are arguments I don't understand very well. But the point is that you can actually have this apparent growth of the Sitter space for a very long time, right? Because S is actually very large for our home universe, it's 10 to the 122. So it means that up to this 10 to the 122 Hubble times, it's actually very hard to tell that your space is being spoofed. But of course, maybe you can look for processes where m is very high, such that it's comparable with the entropy of the universe, then you can detect this. Or you can just wait. Right? You wait long enough. So, quoting John, I think when I talked to him about this, he has this one-line summary that you can only stretch space by so much before it breaks down. Yes?
Should we not expect from the similarity with the interior of a black hole that also has a volume that grows with time, that the relation might be exponential in the entropy?
Exactly.
Good. So, in here, do I have a picture about that? Okay. Here, so the black hole, the volume grows linearly in time. But here, if you look at the exterior, here, the exterior size actually grows exponentially.
Oh, right.
So this is precisely so if I imagine that there is some tensor network where instead of having this exterior that grows exponentially, but something that grows linearly, then from this naive counting you will have e to the s. Okay, so some remarks. Although null states, So the philosophy we're taking here, it may not be true. So the philosophy we're taking here is that there is the fundamental Hilbert space, which is real. It's the quantum gravity user field. And then there is the effective Hilbert space, which is something we think that exists, but it's actually fake. So it is an effective description we write down that is more local and is more convenient for us. So the EFT, which lives in this effective larger Hilbert space, is an approximation of the fundamental process. But the actual physical processes and states always live, they stay within this fundamental small Hilbert space. So if you start in some physical states, you can't really end up in those states.
But that's all the time what people say.
Yeah.
I'm saying.
Yeah, I'm just
starting
wondering.
from semi classical. Yes.
Yeah, exactly.
By it, then you have a fundamental Hilbert space.
Yeah, exactly. So it's the usual thing. I don't have time, so let me just skip this slide. I just want to say that null states are still useful, but even though we don't think of them as real. But to summarize, basically, I introduced for you this concept of overlapping qubits and pointed out some similarities between what's happening on the quantum side and what's happening in the gravity side, and they're very similar in various different regimes. And we can construct these overlapping qubits from non-isometric maps. But this construction is actually quite flexible. We don't have to just use harmonic maps. We can use things like reserved locality, things like reserved energy physics, or really whatever. Right? So I think there's a lot of room for exploration of what should be the right kind of structure to pick for these maps. And finally, we looked at the maritime model. We tried to apply this overlapping qubit idea to this cosmological setting and see that, of course, things can be faked for a very long time, but eventually things break down. As future, I think there are lots of things to think about, and in particular, is there a way we can apply this to quantum gravity and solve our puzzle about degrees of freedom counting in lithography? Or apply to black holes, right? As we thought about earlier, that the timing seems to work out. So I wonder if there's any application in that. There are other things, for example, about the idea of relaxing this macrocausality in various different cases and whether it has any phenomenological observable consequences. Right. And of course, cosmology, and lastly, something about whether, because we can sort of compress do a lossy compression of exponentially many qubits and particularly many qubits, is there some sort of robust property that can be preserved under this compression? And if so, you maybe use it to maybe able to use it to study quantum band-wide systems. So there are many different applications, perhaps in the future. So I think this is a nice starting point for the program and a nice ending point for my talk. So thank you very much.
Questions?
Like you say, you can do this on the other way, as you said, HEP-QIS. You construct HEP-QIS by constructing interior black hole or exterior of the static patch. That's construction, something I work on. And it has this structure. It's already different operators overlapping, but it's exponentially small. So then, of course, those things you construct from smaller to bigger. Bigger to smaller, of course, you have to divide out. Okay. Smaller to bigger is easier. And your last comment? It's like a phenomenology. Yeah, I thought about this, but it's unfortunately even in cosmic impression early on, because we have experimental bound or observational bound, and to be approximate density in our universe impression. It's already at least billion. And E4 you need 60. So it's somehow, even if it's super hyper high energy, it's already extremely good effective. Yeah, I don't know if there's any idea because, but it's not easy somehow. You really want to go very close to that.
Yeah, we should chat about
No, I can see
Or,
what it is, but-
okay. We have some references about this.
Yeah, it's interesting if anybody find that would be really good.
Hi, yeah, so I was also like a little confused about sort of what Stefano asked about earlier, that like the fundamental degrees of freedom are like at the t=0 slice. Should I not think about this tensor network model as being like a holographic model? Or something? Like you're not saying that there's some sort of holographic theory at t=0 or something like that, right?
Yeah, what I really mean is that it's isomorphic to some fundamental degrees of freedom. So there could be some non-trivial mapping from this geometric picture to the more sort of non-local picture.
You said it, yeah.
Yeah, I had a quick question. I was wondering how you found, or how you think about the bound on how many qubits can be smoothed, right? Either either the epsilon squared, or why does the epsilon come into it? Or what is the, yeah, how do you write that bound? Just from the very beginning, and we were just like the bound on the size of the Hilbert space that can be smoothed by
Using the epsilon square. That is coming from some concentration measure argument, which is actually pretty similar to what Jeff and Chris did. And epsilon square sort of happens there from these common elements. But for others, other overlapping maps, we don't actually know what the right relationship could be, right? Because if you deviate from this common mapping, there could be some other relation between capital epsilon and epsilon.
So is that the bound that would apply in the tensor networks that we're doing, or is
Yeah, so
only using carbon?
Yeah, so the Mera tensor network we were assuming is that in the super Hubble scale, you are using the Mera structure. But in the sub Hubble scale, we don't really know what it is, so we use the random. That's why you saw sort of similar.
Any other questions? Okay, if not, let's thank Charles again.